good morning, everyone. So I'm Karol Desnos. I am, as I already told before, I'm an associate professor at INSA Rennes and a member of the IETR laboratory. And today I'm going to present a paper that was published a few months ago in the DASIP conference. The paper was entitled Influence of Dataflow Graph Moldable Parameters on Optimization Criteria, and I think it is a very good fit for this day of the GDRs. The project, this is part of a work that was funded by an ANR project, the project Dark Era, which is about radio astronomy.
C'est un peu loin de mes compétences sur le data.
I think there is a mic. Il y a un micro qui est resté ouvert en distance.
C'est bon, j'ai coupé.
Merci. Since I have plenty of time on the program, just one slide to present myself and what I do. So what I will be talking about today is my main research interest, which is about model-based computer-aided design, mostly with data flow models of computation. So I will talk a lot about it later. This is my main topic of research since my PhD thesis, and more on this in a few minutes. My other research interest includes first image and video coding for machine learning. This is a quite recent interest where the basic idea is that when you have a video that is supposed to be received by an artificial intelligence, you don't really care about the quality of the video. The only thing you care about is the artificial intelligence able to do its task or not. And so by trying to exploit this idea, what we try to do is that we try to use the lossy video compression scheme to try to reduce the size of the video when you transmit it on the network. And we try to reduce it very aggressively. So you try to reduce the quality very strongly as much as possible. So for a human receiver, it would be awful to look at. But for an artificial intelligence, it does not matter. And so this is an optimization problem also, because you have many things to optimize. You can optimize what's happening on the video coding side. You can optimize what you do in the transmission to try to minimize the footprint, the energy footprint that you have for the transmission. And you can also optimize what you do on the artificial intelligence side. How well it will receive the image. Does it have to be retrained? Is it aware of the quality of the video it receives? So you have many things you can tune here and there, and it's a big optimization problem to solve. So this is interesting for me. And then I'm like everyone else, I'm also interested in machine learning. And in particular, I am interested in a new machine learning technique, which is not a deep learning technique, which does not rely on GPUs. It's an artificial intelligence technique called Tangled Program Graph, which is inspired by genetic programming techniques. And the interest of this technique is that this is a very, very lightweight. For an artificial intelligence which is competitive with a deep learning network, you have computations that are 1, 2, or 3 orders of magnitude smaller than the deep learning framework, both for training and for inference. And so we have preliminary results that are very impressive. And recently we have been able to secure an ANR funding with Michael Dardaillon, who is in the room, to fund 2 PhD and a postdoc on this topic. So yeah, I won't talk about this, but this is another research interest. Back to the focus of today. Of course, yeah, feel free to interrupt me since we have time. Feel free to interrupt me during the presentation if you have any questions. I feel that it is more dynamic and I will be able to answer your questions right away. So, like the previous presentation, I am interested in design space exploration. What are we talking about? The input of the design space exploration process is this kind of classical design flow, where you start from a model of the application, you go through a design space exploration tool, and you try to deploy your application on a parallel multiprocessor system on chip, on a parallel target. And you have many things to optimize. The things that are mostly studied usually in the community is the resource allocation. This was the topic of the previous presentation. And you try to allocate the computing resources. You try to allocate the memory of the computing targets. You try to allocate the time of the computation. And the communication links, the security accelerators, and so on. And so this is the thing that we study the most when we speak about design space exploration, the resource allocation of the targets to execute the application. And to do that, usually we have to rely on optimization heuristics, because solving the NP hard problems is kind of difficult. No surprise. And on the target side, there are quite a lot of things that we can also play with when we want to optimize the system. This was the topic of one of the questions for the previous presentation. When you run the application on the target, there are still a lot of things that you can play with, and you can make some decisions during the DSE, the design space exploration process. But some decisions can also be done dynamically when running the application. So you can change the dynamic voltage and frequency scaling of the chip. Sometimes you can also change the hardware. If you have some reconfigurable logic in your chip, maybe you can add an accelerator dynamically, or you can decide at compilation time that you want to add this accelerator or this other accelerator. And you can also play with the scheduling policy, which in non-real-time applications may be completely dynamic. So you have a lot of things to play with also on the target side. The last thing you can play with, and the thing that is usually the less studied, is the application. When you speak about design space exploration, there are a lot of things that you can do also on the side of the application. For example, to solve a problem, sometimes you have many different algorithms that are available, which have different advantages and different drawbacks, and you have to choose. Even when you have chosen one algorithm, there are many ways to model it. Sometimes you can model it in a very sequential way, and sometimes in a very parallel way, sometimes with a good quality of service or a bad quality of service. If it's an iterative algorithm, you can choose how many iterations you want to run. So there are lots of things that you can play with on the algorithmic side. You can also play with the data representation. Do you want to use floating point number, double floating point number, fixed integer values, small integer, like integers, custom floating points? There are many data formats that you can play with, and all of this has an impact on your application. And parallelism, I already talked about. You have a lot of choices on how to model your application, and if suitable, you can have a lot of parallelism or a very small degree of parallelism. These are the things I am mostly interested in this presentation. I'm mostly interested on the application side, because my feeling is that this is sometimes a less formalized thing that you can explore in design space exploration, and the thing that is the less automated. What are the outputs of all these design space exploration process? Many things. Latency of the applications or latency of the system, throughputs, energy, power consumption, memory, footprint, quality of service, security, if we refer to the previous presentation. So these are all the outputs that you want to monitor when you want to optimize your design space exploration. And of course, many of these objectives are antagonists. And if you lower the latency of the system, you will probably increase its memory footprint and its energy consumption. So finding an optimal solution is not feasible, because what is an optimal solution in this context when you have multiple objectives? So this is our problem. This is what we are interested in. And yes, in this presentation, I will be focusing on the application side of the design space exploration, and I will be using as a black box, let's say, algorithms, some scheduling mapping algorithms for the resource allocation of the system. So what are the objectives of the papers? The first objective is to propose a model that makes it possible for the application developer to specify the design choices on the application side, to model them and to give them to the tool for an automated optimization of the system and an automated design space exploration. Then we want to explore this design space. And first of all, we are going to do an exhaustive design space exploration. You will see that the design space that we expose on the application size is not too big, so we can manage to explore it exhaustively for the applications that we have studied. And then, because studying exhaustively the design space that we want to explore is usually not a good idea, we try to give hints on how we could proceed in the future to have a non-exhaustive design space exploration and try to be smarter in the way we explore the different parameters of the application. So what is our input model for the application? I'm a Dataflow guy, so the basic model that we use for specifying the model of the application is the Synchronous Dataflow graph, the Synchronous Dataflow model of computation, which has been around for longer than me, actually. And in this model of computation, the application is described with a graph, which is composed of a set of actors, which are basically functions that you can call. So you can see them as a C function that you call. And each of these actors, when you call it, when you execute it, it will consume a well-defined number of data tokens. So here, for example, the Moldable actor in the middle will consume 366 lines of pixels, and it will produce 364 lines of pixel on each output port. The figure might, on each output port. So this is the model of computation. In order to transmit the data between the different actors of the application, you need a set of first-in, first-out queues that transmit the data from one actor to the next. So this is our model of computation. It's a model of computation that is very well suited to express many forms of parallelism, data parallelism, and task parallelism mainly. And the execution of this model is data-driven. So once you have enough data tokens in an input FIFO of an actor, this is when you can start the execution of the actor. Okay. So here, for example, I know that the split actor produces enough data tokens to start 2 executions of the Moldable actor in parallel. So I have some data parallelism. Okay. On top of this model of computation, something that also has been around for quite some time is a static parameterization. Instead of having a fixed production or consumption rate associated to each input or output of an actor, I can replace this with a set of expressions. So now I have a set of parameters in my graph. So here, for example, I have the height and the width of the images that I am processing in my application. And I have a parameter n, which makes it possible to configure the degree of parallelism of my application. Okay, so n here is 2, so we have a degree of parallelism of 2. And now all the production and consumption rates of the actor are expressed with an expression. And so now I know that the read actor at the beginning of my graph produces a whole image, which consists of h times w pixels. Okay, so now I can easily reconfigure statically as a designer my application. And depending on this parameter, I have a different degree of parallelism. So here, for example, the dilation, erosion, and Moldable actor will be executed n times in parallel, depending on the value of my parameter that is fixed during the compilation of my code. So far, so good? Okay. Now, this model is already quite friendly for the design space exploration, and this is a reason why several of us have been studying it for quite some time. First, the actor firings, the individual firing of actor, is very friendly to study the mapping, the scheduling, and the pipelining of the applications. And so we have been studying it for quite a lot of time. The FIFOs is also quite friendly to perform the memory allocation. The allocation of each of the FIFO in memory can be studied, and you can optimize it very efficiently. I did a whole PhD thesis on this, so yes, this is a very interesting problem. And the last problem is that the parameters in this model, at the beginning of this paper, they require a manual tuning. So usually what we do as a programmer is that we take a model of the application and we try to change the value of this parameter to try to see how well it fits on the architecture. So we change the value of the size of the images that we are managing. We change the degree of parallelism to try to see how well it fits on the target architecture. And this is something that was done manually. And so this is what we want to change. The first novelty of this paper is that instead of having a fixed value for each parameter of the application, we want to have a set of values for each parameter of the application. So now, for example, for the height and the width of the image that is processed by the algorithm, we have a set of different image resolutions that can be used by the algorithm. And the same is true for the degree of parallelism. Now we say, okay, the degree of parallelism of my application can be 1, 2, 4, or 8. These are valid values. I can add some more parameters. For example, I can add a way to activate or deactivate 2 different stages of pipelining in my application. So here I have a first pipeline stage, which I can activate or deactivate with a Boolean value pipe 1. And I have a second stage of pipelining that can also activate or deactivate with a second Boolean value. I can also have another parameter that can control the frequency of the cores. Here, assuming I have a single frequency for the whole system. I can also have another parameter that can be used to control the frequency of the cores on which I am running the application with different values. And with this very dummy image processing application, and with only only 5, 6 parameters, I already have 192 configurations to explore. So I already have a lot of configurations to explore, and exploring them manually would be something a bit tiresome. Here, I have 2 types of parameters. I have the functional parameters, which have an impact on the actual results of the application. So here, for example, if I change the image resolution, I will change the result produced by my image processing algorithm. And so I will probably change the accuracy of my algorithm or the quality of service of my system. I also have some non-functional parameter. So here, for example, the pipeline, the number of stages of the pipeline, or the clock frequency, or the degree of parallelism, they change the topology of my application, they change its characteristics, but they do not have any impact on the result of the application itself. So they are non-functional parameters. They will only impact the design space exploration. Okay, let's continue. So we have seen the input of what I'm trying to do. We have a moldable, yes, I forgot to introduce the name. The parameters with a different possible set of value are called the moldable parameters. So I have a data flow graph with a moldable parameters. I have as an input for my design space exploration process, I have a very simple model of my architecture with the number of cores and the means of communications. And I have some profiling informations that tells me how long it will take to run an actor depending on the different values of the parameters. These are the input of my design space exploration. I feed all of this to my design space exploration framework, which has first to find the best values or the set of values for the parameters of my graph, the moldable parameters. And then I have a classical workflow where I have to apply a certain amount of graph transformation to optimize the application. I do the mapping and scheduling, and I allocate the memory for my application. In the context of this paper, the framework that we have been using is the Prism framework, which is an open source framework that we develop in our team for data flow applications. The output of this design space exploration is a set of metrics for the different solutions that we can explore, for the different values that we can explore for the parameters, for the moldable parameters of my application. And from these values, no surprise, I have a multi-objective optimization problem. I will end up with a beautiful Pareto front of solutions with many dimensions. And since the Pareto front has already been explained, I don't have to explain it again. Okay, let's continue. In the paper, we have studied a few applications. The first one is the Sobel filter, which is more or less the same as the simple applications that I presented in the previous slide. And 2 more complex image processing applications. The first one is a SIFT key points detection, which consists in analyzing an image in order to find a set of key points that can be used to recognize an image and to map an image in another, basically. To compute a homography between 2 images, notably. And the stereo matching application, which is an image processing application, once again, which constructs a 3D representation of a scene from 2 images of a stereo camera, so from 2 cameras separated by a small distance. These three applications have very different complexities. So here on this slide, I am displaying for each application the number of actors in the data flow graph, the number of FIFOs in the data flow graph, the number of moldable parameters in each graph, and at the last information, the number of configurations that we can explore based on these parameters. So here we can see that in the Sobel filter, we only have 500 configurations to explore, while in the SIFT application, we have more than 10,000 configurations to explore. The moldable parameters that we have in this application, a few of them are common to all the applications. So first, we have the resolution of the images that we can process. We have the degree of parallelism. We have the clock frequency and the depth of the pipeline that we can configure. We have a few parameters that are specific for some applications. Notably, we have the maximum depth of the images that we are observing for the stereo matching application. That is a parameter. And we have the SIFT, for the SIFT applications, we have the maximum number of key points that can be detected in the image. And optionally, we can activate or deactivate an upsampling of the image before doing the processing. And both of the three parameters for the stereo matching and the SIFT applications are functional parameters. They have an impact on the quality of the service of the application. So what are our results? So the results that are presented on this slide are for the SIFT application. And here we restricted ourselves to present a result only for a specific configuration of the pipeline, just for clarity of the results. So here we have a latency of 2, which means that we have activated the 2 stages of the pipeline. On the figure, we have represented 3D information. On the x-axis, we have the power consumption of the different Pareto, on the different solutions that are on the Pareto front. We have on the y-axis the throughput of the different solutions on the Pareto front. And on the color axis, we have the memory footprint of the different applications. And as we can see on this example, among the 10,000 configurations that we have explored, we have quite a lot of configurations that are on the Pareto front, and with very diverse values. So, for example, we can see that we have 2 extreme values, one with a very high power consumption, but with a very poor, no, it's the contrary, with a very high power consumption, but with a very good throughput. And another extreme is with a very low power consumption, but with a very poor throughput. So this is just to show one result. Now let's see a bit more of statistics on the result that we have observed. On the 3 applications, the result that I am presenting on this slide is the last result of the table. And this is the number of points, the number of configurations that we have explored that lead to a solution on the Pareto front. So for the Sobel filter, which is the smaller application, 20% of the configurations, 20% of all configurations are on the Pareto front. This is a very simple application, so this was to be expected. On the SIFT key point and on the stereo matching application, only 1 and 2% of all configurations are on the Pareto front. So the takeaway message from this slide is that if you want to explore the parameters, the configuration of the parameters manually, you have many configurations to explore and a very low chance to obtain 1 point that is on the Pareto front. Something that I have to mention is that you select the value of the parameters, but then you go through the whole mapping and scheduling process, which is seen in this paper as a black box. So sometimes you change one value of a parameter, and the result that you have at the end of the mapping and scheduling process is completely different. And it's highly unpredictable from our point of view as a designer of the application. So it's very difficult to know in advance, okay, if I change the value of this parameter, will it be better or worse? Because sometimes you expect that the value of the parameter will improve the quality of the solution. And in the end, because of something happening in the mapping and scheduling process, you end up with a worse solution. So exploring all solutions manually was unfeasible, and we can see that when you explore all of them automatically, very few points are on the Pareto front. If I go back to the previous slide, something that is even more interesting is that while 1% of the points for the SIFT application are on the Pareto front, many points are very close to each other. For example, if you have a look at the blue points in the middle of the curve, you can see that you have 3 or 4 points that are very close to each other. And these points basically are on the Pareto front because they have a slightly different memory footprint. But in the end, with maybe further refining process, we could probably eliminate a few points on this Pareto front and just keep one of them, which is even more, which is interesting. And in this case, we would have less than 0.2% of the point on the Pareto front. So, yes.
It seems that the total number of the points on the other slide is the same. Some 100 points are on the Pareto front. Is it by chance?
It's possible, and I would say it's by chance. Yeah, no, I don't know. It's probably by chance.
Or maybe it's some parameter of the program that selects 100 points.
No. The Pareto front is exhaustive. Okay. All the points that can be on the Pareto front are on the Pareto front. So yeah, no, it might be by chance actually. Yeah, exhaustive design space exploration, never a good idea. So for the Sobel filter, it's quite simple to simulate. So we end up with 1 minute to explore all 500 configurations, manageable. For the stereo matching, it took half an hour, and for the SIFT key point, it took 6 hours to explore all the 10,000 configurations. It's not that long, but still, if you want to change your application design and rerun the whole process, you don't want to spend 6 hours every time you do that. So how can we be smarter? How can we try to be smarter? The basic idea to try to be smarter, and this is still a work in progress, I have to warn you in advance, is that, okay, instead of exploring the whole design space exploration, we will start from this design space where we have all the parameters, all the moldable parameters, and all the values of the moldable parameters. And the basic idea that we have is that, okay, could we maybe start from a few points selected in a smart way from the moldable parameters design space? And from these points, we will have a first look at the metric in the metric space. So we will run the simulation for these few points with the black box mapping and scheduling algorithm, and we will get a first view at the metrics. Then from these metrics, would it be possible to have a classification of the impact of the different parameters on the different metrics? Does it make sense? And the classification that we want to have is that something like this. If we increase the value of this parameter, does it strictly result in an increase on the latency, or maybe a strict decrease in the memory footprint? Something random. When we change the value, when we increase the value of this parameter, the result on the energy is random. Or a last classification is changing the value of the parameter does not seem to have any impact on the value of a metric. So these are the 4 classes possible. And the question is it possible for us from just a few values to try to predict the class? Is there a class first? And is it possible to predict it from just a single value? And if we can do that, then we can go back to the parameter space. And from this classification information, we can try to select in a smart way the moldable parameters configurations that will make it possible for us to find the point on the Pareto front without having to explore exhaustively the design space. Okay, so this is something we would like to achieve. So we didn't achieve it yet, but we have a first interesting result. If we do the classification of the impact of the parameters on the different metrics based on the exhaustive design space exploration, the good news is that we have some classification. We have some successful classification. Not all parameters are irrelevant. So these are the results for the parameters of the SIFT application on the different metrics that we have observed. And we can see that the 4 classes are useful. We have some parameters that have a positive impact on some values, some have a negative, some have irrelevant impact, and some have no impact. So this means that this is something that we can look for. We can look for this classification, and it will help us to find automatically the best parameters in the design space exploration. Now the question is, can we find this classification based on just a few points in our design space? And yes, the answer is yes, fortunately. These are the results for the SIFT steel application. If we just explore 3 values per parameter. So we reduce a lot the number of configurations that we explore. And with just 3 values per parameter, we have a single misclassification. The impact of the number of key points on the throughput of the application is misclassified as a strictly increasing impact, whereas it was an irrelevant classification. If we have a look at bit more at the detail, in reality, the classification is not that bad because most of the time, an increase in the value of this parameter results in an increase of the throughput. In some very, very few cases, it results in a decrease. So the classification for the exhaustive design space exploration is irrelevant, but in reality, if we were to base our design space exploration on this classification, the result would be quite good. Okay, let's have a look at the other applications. So if we take 3 values per parameters, on this slide, what I'm representing is the percentage of the design space that is explored. So 25% for the Sobel filter, 8% for the SIFT key point, and 13% for the stereo matching. So 13% of all configurations have been simulated. And I am representing the number of errors that we did in the classification process. And so we have 0 error for the Sobel and the stereo matching, and only 1 error for the SIFT. If we add the 4 values for all parameters in the SIFT application, we explore 20% of all configuration, and we have 0 error. If we lower the number of points explored to 2 values per parameters, we end up with 0 error for the Sobel filter, 1 error still the same one for the SIFT application, and 4 error for the stereo matching application, with only 2 and 4% of the design space explored. So this is very good news. This means that we can classify quite efficiently the impact of the parameters on the metrics when exploring a very small part of the design space. And unfortunately, this is where we had to stop because the PhD student finished his PhD and the master student didn't want to continue doing a PhD. So yeah, this happens. So as a summary, the result of this paper are that we have proposed an extension of the data flow model of computation to introduce the moldable parameters to specify and expose the design nodes from the applications to the design space exploration framework, both for functional and non-functional parameters. Then we have tried the design space exploration in an exhaustive way, fully automated within the framework, and we have shown that basically less than 20% of the points are on the Pareto front, and for big application, it is less than 1% or less than 2%. And last but not least, we have shown that classification of the impact of the moldable parameters on the different metrics is something that is probably a very interesting thing to look at for the future, and to try to automate the design space exploration in a smart way to try to find the Pareto fronts without having to explore too much points in the design space exploration. Everything is implemented in the Prism framework, which is open source. You can find it on GitHub. And oh, black screen. No, it's okay. And if you have any questions, I will be happy to answer it. And thank you for enduring me. Yes.
How do you do the classification? So find the parameter.
Yeah. Basically, the thing that we do is that because you explore exhaustively, when you explore exhaustively, you consider that you fix the value of all parameters except the one that you are changing, and you do that for all configurations of all parameters but the one that you are evaluating. And you have a look at, okay, when I am increasing the value of this parameter, what is the impact on these metrics? So it's a kind of a complete ablation study, kind of. And for the non-exhaustive exploration, we do the same. So you fix all value of all parameters, and you have a look at the impact of a single parameters on the metric.
Yeah, no, I mean, how do you like quantify the influence of the change of every parameter on the results? So I was thinking about using neural networks for.
We didn't do that.
Okay.
The classifications that we have is just the one that we showed. Is the impact positive, negative, or irrelevant, or no impact at all? We didn't try to fit. This was our objective at the beginning, but depending on the parameters, the impact can be quite different. For some application, you have an impact that is positive, but that is mostly steady and sometimes increasing. In some other application, in some other parameters and metric, you have an exponential behavior, and identifying the functions relating the parameter to the metric is out of scope of this paper. This is something that would be interesting to look at, especially based on the exhaustive result. This would probably be easy to do, but we didn't do it due to lack of time, mostly.
Is it long to do the classification?
No. The classification is a MATLAB script. It takes a few seconds to run. You don't have that many points, actually. Even when you have 10,000 configuration, it's a big CSV file, but exploring it with MATLAB is not that long.
So what is the how much time did you lose? So is it quicker to do the classification part? And how long did you take to complete it?
I don't know the exact.
Not only the
yeah.
Sorry, not only the classification, but the whole process with WN equals 3 or 4. You have
to try different values.
Yes.
The most of the time is spent on the simulation of the system when you simulate the different value of the parameters. So the 6 hours and so on that we showed in the exhaustive part. Basically, okay, yeah, this is what takes the most time. I don't.
Okay.
I'm not sure I got the question. Sorry.
What is the speed up of using the classification?
Okay.
For the whole process?
Basically, if you explore 1% of the design space or 2% of the design space, you have 1% of 6 hours. So yeah, this would be the. Okay, to be fully honest, we didn't have to do it because we already had the exhaustive results. So for us, it was easy to just take the exhaustive result and simulate the exploration with just 1 or 2 value of the parameter while ignoring all of the other values that we have in our file. So, but basically, if you explore just 1% of the solutions, you will spend 1% of the exploration time that we had before. So it will be very, very fast, basically a few seconds to a few minutes maybe, but it will be fast. And I have to mention that Prism is not the fastest tool in the market. So it's coded in Java, so it is quite slow. So we could go a lot faster with something implemented in a smart way in a C++ or something like that. Yes.
For the classification, you say you don't try to fit exponential or something. But do you look at the trend, or if for one solution it is different than the trend, then you have a cross.
Yeah, absolutely. This is a strict classification. So this was the case of the misclassification for the SIFT. Basically, very, very few points did not follow the strictly increasing trend. But in this paper, this is the same. We don't consider just to stay simple, we don't consider the statistics, and we just say, okay, we wanted to have this simple message. But clearly there is a lot to explore here by trying to identify the functions linking a parameter to a metric, or by identifying outliers, let's say in a classification, to try to make a more efficient classification, or that could be trusted to find the Pareto front. And then of course we need to actually close the loop to go back to the Pareto front, but yeah, we have to find someone to do that.
And it means that when you have 4 errors, it will be 0.
Possibly, yes. If we consider the outliers, the 4 errors are probably a misclassification that are honest misclassification that in reality, if you trust them to find the Pareto front, it's highly probable that you would actually be able to rely on this information to find the actual Pareto front.
Thank you.
Felix? Oh, you had a question. Sorry.
Yeah. So actually, when you do the classification, then you modify actually when you modify a parameter, the others are fixed. I mean, there will be maybe let's say an effect where a parameter compensate actually the bad effect of another.
Potentially, yes. Yeah. Well, sometimes I don't know if you increase if you play with the parallelism parameter and the pipelining parameter, if you increase the parallelism and at the same time you decrease the number of increase the parallelism and decrease the number of pipeline stages, the two can compensate each other. Absolutely.
But in the work actually you fix the others and then you.
When we study two values per parameters, we do the Cartesian product of these two values. So if you have three parameters with two values, you do the Cartesian product of all the configurations. You still explore a few configurations to do the classification. Okay. And based on these configurations that you have explored, then you consider, okay, when these two parameters are fixed and the third one is moving, what is the impact? Okay. But you still have to play with it.
Yes, the models in this model, in fact, you have you say you have moldable values.
Yeah.
Is there a linear function, or what is the form? Where it comes from? It comes from application, or it comes?
The values that you put in the model, you mean?
No, the model, the functions of the initial function of the number of tokens. You consider linear functions of n of h.
No, we consider the functions can be anything. They can be nonlinear. So we have some functions with which activate or deactivate, so which are completely nonlinear with.
It comes from the application.
It comes from the applications, yeah. The designer.
So only right function, the parameters probably, or all the values are put in, or you have to choose. You have to decide which values.
At the moment, the values are given by the designer. So you have to design the applications in a way. For example, let's make it simple. The degree of parallelism is related with the height of the image. You need the image to be dividable by the degree of parallelism. And these values were chosen by the designer. So here, for example, in my applications, I know that all the image resolutions that I'm giving can be divided by 2, 4, and 8. And this is why I can give this value to the degree of parallelism. At the moment, we have no relations between the parameters. We just have a set of values for each parameter.
And the value, you can change the value of the parameters, and it does not influence, for example, on the duration of each actor?
It can. Yes, it can. It can influence the energy consumption and the duration. For example, if you change the clock frequency, or if you change non-functional parameters that influences the number of iterations that is happening inside an actor, then in this case, you would actually have a variable duration for the actor.
And the duration
are parameterized. So there is an expression based on the profiling that this is something that you need to do before, but you need some kind of profiling and you need to have a model of the runtime of the actors depending on the values of the moldable parameters.
And have you tried to consider hierarchical?
Not yet. No, we have the hierarchy in the model of computations, but at the moment we haven't tried to exploit, let's say, the hierarchy of the data flow model and the expressions to do that. Something that could also be done actually would be also to study the expressions themselves, to study the expressions on the ports to try to see their influence on the actual parallelism of the graph. There are some things that could be analyzed analytically, but in our case, we wanted to have a black box kind of system where we just put the values, select the moldable parameters value, and try to identify the impact considering a black box system.
You need a function. You need a function. You need to be able to compute all the.
Yes. But this is, we consider that this is an input that can be provided or that can be easily profiled from.
The number of
The number of inputs? Okay. Okay. Yes?
I have another question. So, if I understand the steps, you do first the random exploration,
Mm-hmm.
then you classify, and then you do a reduced exploration.
Yeah.
Can you consider to add some classification state during the reduced exploration, like to you trust the first classification and you want to check if it is still relevant?
Yeah. As I said, we didn't close the loop. This is the plan that we have, but unfortunately, the last arrow go back from the classification to the selection of the parameters. It was not done. So yeah, completely. I think this is a baseline, and there are many things that could be done, and this is something, of course, that could be interesting. You could also try to refine, and instead of simulating new configurations, sometimes based on the configuration that are already explored, if you are in a close neighborhood of these values, you can infer using a Krigage technique. You can sometimes try to infer without simulating the process. You can try to predict some values of as a result of the simulation process. So you could actually sometimes try to skip some simulation using some further mathematical techniques. But yes, of course, I think the process could be something that you refine, and you select the first point at random, and then iteratively you try to refine your model of classification to try to be smarter when you look for the Pareto front. Definitely, this would be a very good idea. Yes.
When you reduce the business case exploration after classification,
yeah,
how do you choose your relevant values for parameters?
This is something that we didn't do, basically. So if someone wants to work on it, and please contact us. We would be happy to continue the work. We don't have a PhD student on this topic at the moment, unfortunately.
But I think that there are some techniques to
definitely
to set initial design.
There probably is definitely. And even the way we explore the initial point, at the moment we have taken, basically when we take 2 points, you take the 2 extreme values of each parameters. When you take a third, you take one in the middle, and you try to distribute the values to better classify the impact of the parameters on the value, on the metrics. But even in this topic, we could be smarter. We could try to use the many things that exist in the mathematical domain and in the optimization research domain, and there would be probably a much smarter way to explore fewer points in the design and to produce the same classifications. So once again, there are many things in all the steps that we have shown. This is a baseline with exhaustive exploration, and many of the things can be explored. We were just wanted to show, okay, there seems to be a possibility here to do things in a smart way and to explore things in a smart way. The interaction also with the mapping and scheduling processes would be interesting. Here we consider it as a black box, but probably you can find some relationship automatically between the parameters and the applications and the metrics automatically in a much smarter way. So this is the dumb way, the baseline dumb way, and then okay, there are many things to explore, and yeah, this would be one of them. Thank you.
Are there any online questions?
The connection.
Yeah, you are still here.
Yes.
No?
No question?
No questions, thanks.
Okay. Thank you very much, Karol, for this energetic presentation. I should also mention that Karol wake up very early this morning to be here. So thank you very much.